Let's resume 5.2, probability distribution. Please recall that we did a bit of cheating. Instead of trying to define what is so-called a probability distribution, we did something awkward. We are trying to establish these two concepts, probability mass function, which we did in the previous video, and the cumulative distribution function, which we will do in this video, and then put those two together, and that's what we are going to refer to as the probability distribution of a discrete random variable. One part, mass function, is done in the previous video. Let's go over to the cumulative distribution function with an example. Okay, let's go back to the same type of example here, an urn model, 5 red, 3 green, 2 blue balls out of total 10, and let's find out distribution functions. The first one, capital X, it can take 0, 2, or 3. So how do we get the cumulative distribution function? Well, let's see. The probability mass function is as follows here. We saw that, and then we checked out the graph as well, because these three values, 0, 2, 3, are the allowed values, otherwise impossible. Now let's produce distribution function. When x is less than 0, then when x is less than 0, then it is impossible to have any accumulation up to that. I mean, this is a probability cumulative distribution function here. This one is. And what is the probability that x takes a value less than or equal to x, where x is less than 0? Oh, that's a bit confusing. That's equivalent to probability of this capital X taking a value less than 0. But that's impossible. It can take only 0, 2, or 3. It cannot take a value less than 0. So that's impossible. So probability for that case is 0. Now, between 0 and 2, including 0, this one kicks in. 0 is possible. So the probability of this random variable capital X taking a value less than x, where x is between 0 and 2, so less than or equal to something like 0, less than or equal to 0.5, less than or equal to 1.69, less than or equal to 1.99, those kind of things, all includes just the red ball. When x equal to 0, only that part, only this part. Only the red ball kicks in. And then when x reaches the next interval between 2 and 3, including 2, now the green ball kicks in. And consequently, we have to accumulate, add up the probability, and then we get 4/5. We have to add 1/2 and then 3/5. We have to add up because this is accumulation. 0 kicked in and now 2 also kicked in. When x is less than or equal to 2, less than or equals to 2.5, less than or equal to 2.99, all those kind of things include these two. Or if you look at the both directly, these two. And finally, when x is greater than or equal to 3, then blue ball also kicks in, because now probability that capital X is less than or equal to 3, less than or equal to 4, less than or equal to 3.59, less than or equal to 5,000, whatever that is, we're gonna get all three of those. Blue ball also kicked in. Consequently, we have this kind of accumulation. We have to add up the probability. So first, we begin with impossible, 0, and then the first one kicks in, and then the next one also kicks in. So we have accumulation of these two. And then the next interval, third one also kicks in, and we have an accumulation. In this case, there is no more, but if you have more colors, then we'll have more increase. If you draw a graph, it will be something like this. As a step function, it increase, kind of like this. From 0 all the way up to 1. Pay a little bit of attention to the end point. This end point is included in the next interval. This part is hollow. This one is solid, that's hollow. This one's solid, that's hollow, and so forth. Because 0 is included, x equal to 0 is included in the next interval. There's a bit of a subtlety there. Well, I hope everybody could follow, but let's get realistic. This is not the kind of thing that everybody can get just like that by just doing one example. So let's continue with a couple more examples. We have time. Okay, let's begin the next example. Let's consider this random variable here. Y can take negative 1.5, 0.5, or 1. In this case, here goes the mass function. When y can take x equals negative 1.5, that means red ball. When y takes 0.5, that means the green ball. When y takes 1, that's the blue ball. Otherwise, no other color exists, so they are all impossible, so we have 0. So that's the mass function. How about the distribution function? Oh, before that, let me show the graph of it. We have those red, green, and blue dots. Those are the probabilities of these three x values, otherwise all 0. Now, what is the distribution function? Well, we have to look at, okay, let's hide a little bit. This function, probability where capital Y is less than or equal to x. Now, what if x is less than even the smallest possible value? That means y takes a value less than negative 1.5. That's when this one is less than, x is less than negative 1.5. And that's impossible. It can begin with negative 1.5 and on. So what's that probability? 0. And then at x equals to negative 1.5, red ball kicks in. Between negative 1.5 and 0.5, red ball kicks in, and then we have the probability 1/2. Now, next, at 0.5, green ball kicks in, so between 0.5 and 1, we have this accumulation, 1/2 plus 3/10, we get 4/5. And finally, at x equals to 1, we have blue ball as well. Blue ball always also kicks in. Consequently, when x is greater than or equal to 1, we have to add up all three probabilities, which is 1. That's the biggest possible. Here is the graph. As you can see, we have increasing step function 0, and then here's the first jump at x equals -1.5, the next jump at x equals to 0.5, and the final jump at x equals to 1. These three breaking points, which correspond to these three x values of mass functions. Whoops. Okay, I hope that is enough, but just in case, let's go over to one more example. We have time. Let's consider this example. Let's consider the cumulative distribution function of the third case. We have two possible z values, right? -1.25. At that point, both red and green balls kick in. The probability will jump up 0.8. And then another 0.2, the blue ball will kick in at 4.75. Here is the mass function. At these two cases, -1.25, then the probability is either red or green, so we have 4/5. When x equal to 4.75, blue ball, so we have probability 1/5. Otherwise impossible or 0. And here is the graph of the mass function. Okay, how about the cumulative distribution function? At before -1.25, impossible or 0. There's no accumulation. At x equal to -1.25, this will kick in and go on all the way up to 4.75, so in that interval there. After 4.75, blue will also kick in, so sum of these two, that accumulation, you're going to get that kind of step function. Here we go, and here is the graph. Less than -1.25, which means there's no legal value z can take, so that probability is 0. At x equals to -1.25, both green and red balls kick in, and accumulated probability will be 4/5, all the way up until 4.75. At x equals to 4.75, blue ball will also kick in, so accumulation will be total 1. And that's how we get the cumulative distribution function. In this video, we discussed probability mass function and cumulative distribution function. We can do something similar for a little bit more complicated systems as well, and that's going to be the topic of the next segment of the video. And one more. By the probability distribution of a discrete random variable, we're going to mean by its probability mass function and the cumulative distribution function put together.